Hi everyone, this is Dr. C. Labesh Kumar from Department of Mechanical Engineering. So I am going to uh, explain about the finite element analysis. In earlier classes, also we have learned about one-dimensional analysis. Now here we are going to learn about plane truss element. So how this plane truss element will be. So at each node, 2 degrees of freedom will be available in plane truss element. So let us see about plane truss element. So it will be coming with respect to CO2, make use of shape functions of truss and beam elements for obtaining stiffness matrix and load vector to compute nodal displacement of the stresses. So let us see what is a plane truss element. So plane trusses are elements which are oftenly used for construction, particularly for roofing of residential and commercial buildings. And also it is helped for short span bridges. So wherever the bridges are necessary, these are the supports upon which these elements are being placed. These elements are nothing but called as a truss element. So these trusses are those elements which are used for construction as well as residential roofing, where they required different material to be hanged over on these truss elements. So whether there are 2 or 3 dimensional belongs to the class of skeleton structures. These structures consist of elongated structural composites called members, so connected to joints. So each these are called joints and these are called members. So generally in our language in FEA it is called as node and this is called as element. So this is distributed in this format. So a plane truss structure will be in this format. So a plane truss element consists of members and as well as joint. So skeleton structures can be analyzed by different varieties of method. In that hand oriented methods are there as well as displacement and force methods. So they can be analyzed by using computer oriented FEM. So this versatility makes this structure a very good choice to illustrate transition from hand calculation methods to undergraduate course. So a fully automated FEA produces a good commercial package. So the characteristics of a truss member is a very good understanding for joint displacement when the loads are acting on the member. Neither they have a horizontal or vertical, although they are resolved in horizontal and vertical components. The joint displacement of the loaded truss member are generally neither horizontal or vertical. So they are always inclined. The truss member will be always in inclined position. So they are neither horizontal or nor vertical. They are being inclined and can be resolved both in horizontal as well as vertical. Next, the second property of the truss element is that they are subjected to compression and as well as tension types of loads. So either we will do compression at the corner, around the body compression, one side compression, other side tension it will take. The pin joints are used to join the truss elements. So the structures are very different. So this is one of the truss element. So if I say this is one truss element, so these are all called as pin joints and these are all members. So the pin joints are used to join the truss elements. Generally removable pin types of truss elements are used to join the truss elements. So a truss structure consists of only 2 force members. So 2 force members are consist of these truss elements. So that is very every truss member is indirect is undergoing into tension or compression. Suppose this is a truss members. So when I apply load on the truss element, so it will be either will form into compression format in this area or tensile format in the other area. So that is the property of this truss element. In truss, it is required that all loads and reactions are applied only at the joints. Joints are nothing but these pins, and at their ends by frictionless pin joints. So here whatever we learn in trusses will be without any friction. That is called frictionless type of pins, where the body will not have any friction when it is under the load. So that is what happens in a truss element. So let us see the stiffness matrix for the truss element. It is very huge matrix because for every node we have 2 degrees of freedom in x direction as well as y direction. Thereby, the matrix of K will be in the 4 by 4 format. So first let us consider a pin joint which transmits force only in the members either subjected to compression or tension. The loads are applied at the joints. Suppose these are the loads which are applied at 2 and 4, and these are all members related to that truss element. The loads are applied only at the joints. Finite element modeling of the truss identifies joints as nodes and members as the element. So I have already informed you that element and nodes are how we categorized any discretization in a FEA model. So now, if we consider a single element or single member, so this is x direction and this is y direction. So this is a truss element which is neither horizontal nor vertical. Now 1 and 2 are the nodes which are in the space, and this is the member. Now if I apply force at point 1 as well as point 2, that means load application, the point 1 will move in the horizontal direction in this format and the vertical direction in this format. So at each node we have 2 degrees of freedom in form of Q1 as well as Q2. Similarly, Q3 and Q4. So this is the deformed element. After deformation, this is before deformation element, and this is the after deformation element. After deformation element, you can see there is a slight differentiate in the length of the truss element. Now, we can resolve this equation by Q1 dash is equals to Q1 cos theta. So if I consider this as a triangle, if I consider this as a triangular element, now I can segregate this in Q1 dash is equal to Q1 cos theta plus Q2 sin theta. Similarly, if I want Q2 dash, so Q2 dash, Q1 dash are the displacement at nodal 1 and at nodal 2. So Q2 dash is Q3 cos theta, local displacement, global displacement. These are local displacements, and this is the global displacement for the node A and B. So that is what I am saying, that for each node there will be 2 degrees of freedom. So 2 degrees of freedom in the form of Q1, Q2 at node 1 and Q3, Q4 at node 2. Now we will see the matrix formation. Let Q1 dash and Q2 dash be the displacement of node 1 and node 2 respectively in the local coordinate system. So thereby we can write this equation as Q dash is equals to Q1 dash and Q2 dash. If I furtherly expand this Q1 and Q2, the displacement vector can be written as Q is equals to Q1, Q2, Q3 and Q4. At node 1, we have Q1 and Q2. At node 2, we have Q3 and Q4. Thereby, the relation can be given as Q1 dash is equal to Q1 cos theta, Q2 sin theta. Similarly, Q2 dash is Q3 cos theta, Q4 sin theta. So now what is happening in the direction cosine, I will take LM as a direction cosine. I can write L is equals to cos theta and M is equals to sin theta or cos phi, cos theta and cos phi, thereby which is equal to sin theta. Cos phi is nothing but minus cos theta. So sin theta. So L is equals to cos theta and M is equals to sin theta. So I will replace these cosine values in the equation so that we will form a matrix. So now Q dash is equals to L into Q. So this L into Q is our direction cosines for angle x dash as well as y dash. This can be written in the form of L is equals to LM0000 LM. So LM stands at node 1, LM stands at node 2 at the final values, but 1, 2, 3, 4, 1, 2, so the third column and fourth column, the first row will be 0, as well as first and second column, the second row will be 0, because we need to form a symmetric matrix actually here. Now, let us consider 1 and 2 as an element. You have x2 minus x1, y2 minus y1 distance. So, we have L is equals to cos theta, which is x2 minus x1 by LE, the length of the element. M is equals to sin theta, which is y2 minus y1 by LE. So, if I want to find the hypotenuse, it will be the distance between 2 points, that is x2 minus x1 whole square plus y2 minus y1 whole square. So, by substituting all these differences in the equation, I will find the K matrix. So, I already know that the K matrix for one-dimensional element is AE by L, 1 minus 1 minus 1 and 1. AE is nothing but cross-sectional area, E is the Young's modulus. Now we need to substitute all the above relations, that is Q1 dash as well as Q2 dash in the relation, so that I will get a K matrix. So in general, we know that strain energy U is equals to half QT and KQ. So K is nothing but LT, KL and L. So L, we already know that L matrix is LM 0, 0, 0, 0, LM. So substitute L whole trans. If I do transpose, it will be 1 by 2 will be 4 by 2 will be 2 by 4. That's it. Thereby, what I will get is L M 0, 0, 0, 0 LM. So this multiplied with respect to this matrix with respect to Q, thereby I will get a matrix which is called as stiffness matrix for a truss element. Stiffness matrix for the truss element. So thereby the equation AE by L, that is 1 minus 1 minus 1 1, can be written in the form of AE by L. E is the Young's modulus, A is the cross-sectional area, L is the length of the element. L square, LM and M square. This is one matrix. Minus L square, minus LM, minus LM, minus M square. Minus L square, minus LM, minus LM, minus M square. L square, LM, M square. So this is what our diagonal matrix is. So if you see it very carefully, instead of 1, we are going to have L square, LM, M square. 4 components, 1, minus 1, minus 1 and 1. If I multiply this whole component with respect to 1, I will get L square, LM and M square. Similarly, if I multiply this component with minus 1, I will get minus L square, minus LM and M square. Similarly, the same if I follow the diagonal principle, that is minus L square, minus LM minus M square, and L square, LM and M square. So this is the matrix what we have derived for a truss which has 2 degrees of freedom at each node. The elemental stiffness matrix are assembled in usual manner. The usual manner is nothing but we are going to add it in diagonal. So I already explained in the previous sessions that if you have 2 matrices, you need to add it diagonally, thereby to get K is equals to K1 plus K2. So similar process we are going to use to add K matrix in the truss element. So the truss element will have a major factor on the derived equations. So the computer logic for direct placing element stiffness matrix in global stiffness matrix for a banded and skyline solutions can be learned in the coming classes. So thereby, the only derivation we have a very much strong flexibility for elemental stiffness matrix is K matrix for truss element. The truss element is a one-dimensional 2 degrees of freedom at each node, that is in x direction as well as y direction. So if this is the element, it has x direction, y direction, x direction, y direction. This is one node, this is second node. I have Q1 dash, for this whole displacement and q2 dash for this whole displacement. By displacement along x direction I will give q1, y direction I will give q2 at node 1. Similarly, at node 2 x direction I will have q3, at node 4 I have, that is y, which is q4. So this is at node 1 and node 2. At node 2 x displacement, at node 2 y displacement, at node 1 y displacement. So these are local displacement. Global is q1 dash and q2 dash. So thereby I will have the relation for this. Okay, thank you for
Like, share and subscribe. Hit the bell icon for more updates.